Okay guys, so from last year we had a variety of parent functions whose graphs you need to be familiar with. And that's going to be the same is true for this year as well. We're going to add a couple to that list, but you should recognize a lot of these. I'm going to go through each of them and give you the equation and then show you what the graph will look like. What I want you to do after you copy down the equation and the graph to go back and figure out the domain and range of each of the functions. Okay, so the constant function, that's just y equals some sort of number. So no variable over here. I'm just going to give you like an example. For instance, y equals 5. And that is a horizontal line. So that horizontal line can move up or down depending on what number y is actually equal to, but fairly simple parent equation. So either at the end of this video or right now you can pause it, think about what the domain and range of this particular graph would be. Now let's go over to absolute value. That equation is y equals the absolute value of x. And there's a couple key points that you have to know in this graph. Every time you graph them, I want to see these points. This has a point at 0, 0, 1, 1, and negative 1, 1. And we have this V-shaped graph. Now I make you put these points on here so that when we start moving this graph around, I can see how you're moving those points around. Once you have those points, you just got to make sure you have this V shape. You can put more points on the graph. That's fine. You could put a point at 2, 2 and 3, 3, but you have to have at least these points. The linear function, something like y equals x. That's the most basic linear function. Now, we know that we can put a slope in front or add a y-intercept there, and that will change what the graph looks like. But the most basic linear function looks like this. 0.3, 0, 0, 1, 1, and negative 1, negative 1. So you've got to have those points, and it's just a perfect diagonal line. And then one of my favorites, the quadratic function, y equals x squared. And that has the point 0, 0, 1, 1, 2, 4, and then negative 1, 1, and then negative 2, 4. And you may remember, this makes that nice parabola shape. Okay, so let's go to the next page. The square root function, y equals the square root of x. That has the point 0, 0, 1, 1, and then 4, 2 on it. And looks like so. My graph might be a little off there, but general idea is correct. Again, make sure you're showing me those points. The inverse function also goes by the name rational function. So we'll put that name up there too. Y equals 1 over x. And this one is fun because it has asymptotes. We have the asymptote on the y-axis and on the x. It has a point at 1, 1. And it's curvy, but it sort of tucks in the corner there. And it has another part at negative 1, negative 1. And again, sometimes people make this a very jagged graph, like they make this a perfect right angle, and that's not what is happening there. There's a little curve to it. Okay, the cubic function, y equals x cubed. Has the point 0, 0, 1, 1, and then we can add another one, 2, 8. And same thing in the other direction. looks like so. Has a nice little squiggle there to it. Inverse squared, y equals 1 over x squared, has two asymptotes. Also, this goes by the name rational squared function. Sorry, I realize you can't see that. Rational squared. Okay, so this graph has the point 1, 1 and negative 1, 1. And looks like this. So it's a lot like the one above it, except that second part is in quadrant 2. A lot of people think it looks like the old video game systems symbol, the Atari symbol there. So if you are familiar with that, that might help you remember it. All right, last page. Exponential growth, we've encountered these already. Y equals, we'll keep it simple, b to the x, but b would have to be bigger than 1 to be a growth. Has the point 0, 1, asymptote right on the x-axis. There you go. Now this general shape will be true anytime this number up here, b, is bigger than 1. Let's go down to the next one, which brings us to exponential decay. Same idea, except b is between 0 and 1. Still an asymptote. Still a y-intercept at 1. But this one starts to up really high and quickly decays or decreases. Okay, and then the step functions. So the rounding up function, y equals the rounding up of x. Okay, also called the ceiling function, so if you called it that, that would be fine. And I always kind of recommend making a little chart for this to help you out. It's one of the parent functions that I do not try to memorize. I pick 3 numbers, 0, something between, bigger than 0, and then less than 1, and we kind of see what happens. If we plug in 0, we get 0. So I know that that point is on this graph, so I get to fill in that point. 0.5, if I plug it in, rounds up to 1. So I'm going to estimate where that is. It's about right there. And then if I plug in 1, that's at 1. So you have to remember that these look like steps, but it's hard to remember where to draw the steps and where to make the closed circles. So if this is a closed circle here, above it would have to be an open circle. If this is a closed circle here, above it would have to be an open circle. So I think that helps you see, oh, that step has to be right there. And then you kind of just go with that pattern. Now you can see I made this coordinate plane kind of magnified so that it's easier to draw the steps. You can't draw them all. You can't do this forever, so eventually you have to say enough is enough. If you draw, 2 in the positive and 2 in the negative direction, I think that that's fine. And then the rounding down, or the floor function, so again, I like to make a little chart just to help me remember. Zero would stay at 0, 0.5 would round down to 0, and 1 would be at 1. So we can plot some points. 0, 0, filled in. 0.5, 0, which would be about right here, and then 1, 1, which would be here. So what this ends up doing, if you see that these two dots are on the same line, that's got to be a step. This dot is filled in, so right below it would have to be open. And then we can just kind of keep that pattern going. Do a couple in the positive direction and a couple in the negative. That's that's pretty good, I think. Okay, so, oh, I just realized you can't see my steps. Sorry, let me go over that one more time. We did our little chart. 0, 0 was a point right there. 0.50 is a point, that's right there. And then 1, 1 is a point, that was right up there. These 2 points were on the same step, so that's where a step had to be. If this point's filled in, that point below it would have to be open. Otherwise, it wouldn't be a function. Okay? Alright, so make sure before you come in tomorrow into class that you have answered the domain and range of each of these. I just want to give you a little extra practice with domain and range. But I'll know that you haven't listened to the video if you don't actually have that part filled out. Alright, sounds good. See you guys tomorrow.